Well, thank you all for joining another lecture for interactive computer graphics. So this is going to be a fun one today, I'm hoping. Now, today's topic is going to be related to what we talked about last time. Last time we talked about global illumination. Today, we're not going to talk about global illumination per se, but we're going to talk about something that's closely related. That's going to be ambient occlusion. And then we're going to talk about soft shadows. So we're going to spend quite a bit of time on this topic that's called ambient occlusion. So let's start with that. Ambient occlusion. All right. What is it? Why do we need it? All right. Of course, as usual, we are going to start with the rendering equation, right? You've seen this before. You're familiar with it, right? So the outgoing light is a function of an integral over all incoming light from all directions over this hemisphere, multiplied by the geometry term, multiplied by the material function that is our BRDF. All right. So this light, this is the difficult term here, incoming light. Computing that is the difficult term, right? Because that involves direct illumination, which is easy to compute, and indirect illumination, which is not easy to compute. So this was the whole difficulty of global illumination was coming from this term, right? And the way we computed global illumination was that we wanted to use different techniques for direct illumination and indirect illumination. So we separated this integral into two integrals. One was handling with direct illumination, the other one is handling indirect illumination, right? And with that, we said, hey, if I have just a single light source in my scene, this integral collapses to this simple form. Or if I have multiple finite number of light sources, which I often do, then I can just do a sum over those light sources, and that part was fine. Now this indirect illumination, that was the difficulty. So with global illumination, when we were handling global illumination, this is the part that we were sort of struggling with. So what do we do? I don't want to solve this. That's the truth. Okay, I mean, I need to solve this to get proper realistic lighting, but that's way too expensive. Can we do something that's simpler? That's the question, right? So what we're going to do is that we're going to approximate this indirect illumination as some ambient light that exists in the scene. All right, I'm replacing this indirect illumination as some ambient light. So what is that ambient light? We've seen that ambient light before, right? We said that in the very beginning, you'll remember when we were doing very simple shading, we said we should have some ambient term. And that ambient term, we said, oh, that's just going to be a constant amount of ambient light. That's what we did, right? So what happens if I take that constant ambient light and just put it into this equation? What do you think happens? Well, you'll see that when I put it down here, what's going to happen is that, well, this term does not depend on the incoming direction, omega, right? So it just goes out of the integral. Now I have these terms here that don't depend on lighting. It just depends on the material, and this is the geometry term, right? It just only depends on the material. So I could just pre-compute it and call it whatever that is, right? So I can just say, I'm going to have a material property that tells me what this integral is. Let's call it Ka. Does that look familiar? That's exactly what we did, right? We said we had this, we had this ambient term in our material as a material property. That's why I call it a red. So that's our material property. So using that, we had this ambient term. So what it did was that it allowed us to go from an image that looked like this, where this side was completely pitch black and you couldn't tell where the sphere ended, to this image where you could sort of see where the sphere ended, but it was just a constant flat ambient, right? So no ambient versus ambient. That's what we had before. Yeah, I mean, it does what it tries to do, but not that great, right? So let's see, this is a very simple example. Let's see a little bit more complex example here. So look at this scene. In this scene, I have light coming from outside. Light is coming from outside and illuminating parts of this room. Well, in reality, if there's a lighting situation like this light that is hitting something in this room will bounce off of these things and illuminate the rest of the room, right? We talked about global illumination, so that's exactly what happens. Light bouncing off in the scene, so it's going to illuminate everything. But we don't have that because guess what we did? We sort of eliminated, we got rid of the indirect illumination term, we got rid of all the ambient term, there's nothing here, right? So everything's gone. I only have direct illumination, that means this is what I get. Not great. Okay, so let's add our constant ambient term here. Are you ready for some magic? All right, we're adding our constant ambient term. Are you ready? From here, we go to here. Yeah, what did you expect? I'm just adding some constant light to everything. So I basically added some constant color to everything. Okay, so let's be fair here. In this scene, I don't have any materials in the scene. Like everything is the same material, everything is the same color. That's why you cannot see any detail, right? But if things were different, had different colors, different KAs or different materials over here, you would start seeing some differences. Like of course over here, only over here I'm seeing this BRDF term. Everywhere else I'm concerned with this KA. So because I have the same KA and same ambient illumination everywhere, it doesn't look that interesting. So with ambient occlusion, we're going to improve this very, very crude and awful ambient approximation. We're going to make it look like something so much better. Are you ready? From here, we're going to go to here. All right, like from here, we're going to go to here. Now, I'm looking at this. All of a sudden, I'm seeing the rest of the room like everything is there. I can see all the details. And still, I'm using the same material. Well, all of the objects here, they're using the same material, right? But I can see them. How is this happening? Because, well, I did not get rid of this integral here just yet. That's how it's happening. All right, it's going to be a little bit more complicated. So, for us to achieve something like this, we're going to take our simple ambient approximation and we're going to add an occlusion term to it and convert it to an ambient occlusion. So basically, I'm multiplying it with this visibility function, or 1 minus occlusion. And this visibility function is a very, very simple function, not a very complicated function. It's very simple. It's either 0 or 1 for any given direction. For a given direction, it's going to be 0 if that direction is occluded. It's going to be 1 if that direction is not occluded. So what do I mean by that direction is occluded? If let's say I'm interested in computing ambient occlusion at this point, this is the point I'm shading. So for any given direction omega I, I'm going to look if there's something along that direction that's blocking that direction. Such as if there's an object here that's blocking that direction, then the value of the visibility function for this omega I is going to be 0. Right? But for some other omega I, where there's nothing blocking it, its value is going to be 1. So by using this visibility term, we will be able to get a much better approximation for the ambient term. All right? And we're going to do one more thing, where we will simplify this BRDF evaluation here, and we're going to replace it with some ambient term divided by pi. Why is this divided by pi coming? You'll see in a minute. It's a normalization term. It's going to be, I'll tell you where this is coming from just a second. This is going to be some constant term to replace our BRDF, just to make things a little bit simpler, so we don't have to worry about the BRDF evaluation. All right, we're trying to simplify things. Okay, so if I take this equation and just put it up here, I get this term. Obviously, this is constant ambient light. So that's going to get out of the equation. And I also have constant BRDF. That's also going to get out of the equation. So this is what I've got. I'm just going to move this pi over here. All right, so this whole thing is going to be my ambient occlusion term. Now, I have this 1 over pi here because if visibility term is 1 for all directions, it sort of disappears if it's 1 for all directions, then it becomes the sum of all cosines over the hemisphere. that sums up to pi. Okay, so by dividing it by pi, you're saying this ambient occlusion term becomes a value between 0 and 1. Right? That's just 1 over pi here is just the normalization factor. So basically, this is what we had before, right? This is exactly what we had before. Now we added this ambient occlusion term. It's a value between 0 and 1, and it will depend on where a particular point is. So if a point is sort of occluded, it's not really visible to ambient light, it's in the crevices of things, it's going to be closer to 0. If it's out in the open, it's going to be 1. Example, here's an ambient occlusion, just the ambient occlusion component, just this, the value of this integral, just the value of this integral shown in a scene. There it is. So as you can see, things that are out in the open, they're just white. That integral evaluates to 1. And things in the corners, things that are sort of hidden from other things, there are lots of objects blocking the ambient light, they're going to be closer to 0. That's going to be black, right? So that's the idea of ambient occlusion. It looks pretty good, right? Just by looking at ambient occlusion alone, I can tell what this thing looks like, right? What this scene looks like. I can see where all the objects are. It's great. Even on its own, it's actually looking pretty good if you ask me. But it's not necessarily, no, it's not indirect illumination, right? It's a very crude approximation of indirect illumination. Obviously not as crude as just a constant ambient factor. It's way better than that, right? It's way better than constant ambient, but not indirect illumination. Nonetheless, if I use this ambient occlusion in a scene, in this scene, just add all the materials and everything, you get an image that looks actually pretty good, right? You know, you could say, okay, this doesn't quite look like a photograph, but it looks really good. Really, really good. It makes a big difference, right? So ambient occlusion basically is great. And you could say, okay, maybe you're not too interested in generating realistic looking images. Maybe you're interested in other things, such as, yeah, you just want to visualize things, like scientific visualization. Here's an example of something. So yeah, it doesn't matter what it is. The point is that I have this complicated shape I'm looking at. There's some colors here. I'm looking at it. Can you see what it looks like? It looks like kind of like a blob, right? You can't quite tell what it is. I mean, the real world objects are things that are familiar to us, and we look at them, you might be able to recognize what they are, even with really simple illumination. So here I'm using constant ambient. I keep saying I didn't render this image. But here we have constant illumination. So it just looks kind of flat, and it's really hard, or if possible at all, to tell what this 3D shape actually looks like. It's not something that's familiar to me, so I have no idea what it looks like, right? But if I just add ambient occlusion, I get this. And all of a sudden, I know what it looks like, right? You look at it and you can tell. Oh, there's this part that's closer to the camera. There's this part, there's a hole in here. It's just, all of a sudden, this whole 3D depth information is obvious, right? You can tell. Let me show you another example from the same database. Here's one, here's the other. Constant ambient occlusion. Right? All of a sudden, you can start seeing these 3D details. So it's actually a very, very powerful thing to add ambient occlusion to visualizations, especially when you're trying to visualize something that's so complicated and it's like impossible to see the 3D data just by looking at it if you don't have ambient occlusion. Like, super powerful. So, okay, ambient occlusion is great. We love it. Let's do that. Let's add ambient occlusion to our scenes. Now, I have a very simple scene here. And this simple scene, I'm going to add an ambient term. Now, if I add a constant ambient term, things got a little bit brighter, right? Just constant ambient. It didn't help at all. All right, so I had super pitch black parts here. well, they're not super pitch black anymore, but okay, I mean, why do I care? Right? It just didn't really do anything. All right, let's add ambient occlusion. Are you ready? I'm adding ambient occlusion to the scene. From here, it's going to here. Isn't that amazing? Isn't it? Not really. I mean, this looks identical to that one. I don't see any difference. Well, there's actually absolutely no difference. This is identical to that one. Wait, what? What happened? Here's what happened. If I just show you that ambient occlusion term, just the ambient occlusion term. For this scene, the ambient occlusion term is this. It's black. Everything is fully occluded. What? It's not very helpful, right? Obviously, if I apply this ambient occlusion to my ambient, I get exactly the same image that I was getting before without it. It's not very helpful. So why is this happening? All right, let's pick a point in the scene. Let's say I'm picking this point. All right, this point. Now what do we do for computing ambient occlusion? I'm going to look at all directions over the hemisphere, right? I'm going to look at all directions over the hemisphere, and I'm going to decide whether or not they're occluded. Now, imagine that this Cornell box scene has a wall in front of it that's covering the front part. Okay? In that case, any point in here is completely covered in a box. So, guess what? All directions are covered, right? So if I compute the ambient occlusion term, the visibility term, for any of the directions over this hemisphere, they're all going to be occluded, so I'm going to have black everywhere. So the ambient occlusion term evaluates to 0. All right, that wasn't very helpful, was it? So we can't quite use that for ambient occlusion. It's not very helpful. So what we're going to do for computing ambient occlusion is that we're going to limit how far we're going to look to decide whether or not a point is occluded, right? So I'm going to pick a size for my hemisphere here. Let's pick a size. So this is going to be my hemisphere size. And for computing the ambient occlusion for this point, I'm only interested in objects inside this hemisphere of this particular size, right? So in this case, I am seeing probably a part of this wall. So that wall is giving some occlusion, but the rest is all out in the open, right? So with that kind of evaluation, I can get a much better ambient occlusion term, right? So I'm going to have a radius, and with that radius, I will only look at things that are within that radius. And by doing so, my ambient occlusion term, it turns to something that looks like this. So you could say, I don't really see any difference. It still looks pretty similar. It is similar, not exactly the same though. It's not exactly the same. Like you should be able to see some differences over there, right? So like it's they're illuminated slightly differently. There are some subtle differences here. It doesn't make a huge difference in this scene. This is a very simple scene, but it makes some difference. And if you compare it to constant ambient over here, right? It's totally flat. Still adds some detail. You see, like constant ambient, all these corners are getting a little bit darker, right? They were brighter, they're getting a little bit darker. Because the ambient occlusion term here looks like this. All right, so it doesn't add too much, but it adds some detail in the scene, because in this particular scene, I didn't really need ambient occlusion that much, but it added some stuff. But obviously, this is not indirect elimination, right? So it's not giving us the global elimination solution. So if I show you the global elimination solution in the scene, it looks like this, right? So this is just ambient occlusion added to direct elimination, and this is indirect elimination. Of course, I could adjust the ambient amount and maybe get something that looks a little closer to this, but we won't get any color bleeding effects. Like on this side, I'm getting sort of greenish wall. Over this side, I'm getting sort of reddish wall. I'm not going to get any of that with ambient occlusion, right? So it's just that occlusion of some constant ambient term. So not indirect elimination, but still pretty good. In a lot of scenes, it's actually very helpful. Now, you might say, okay, global elimination is so much better, and I think I would agree. It is so much better. And ambient occlusion is not all that great. Well, before you put your judgment on ambient occlusion, let me show you one more thing. Sometimes you might even prefer ambient occlusion to global illumination. Here's an example. Constant ambient occlusion, global illumination. Now what's happening here? Well, in this case, the light is coming from all directions, just like the ambient occlusion assumes. But ambient occlusion is like a term that I can control based on what kind of radius I pick. Global illumination involves light bouncing around in the scene and all that really more complicated stuff. If you actually compute global illumination in a simple scene like this, the result may not be what you want. Like over here, I'm seeing a lot more surface detail than here. But obviously, I would say, well, this should be more realistic, although, I mean, it's kind of hard to call this realistic, right? Because it's not a very complicated material model or anything. So, yeah, this is exactly what the light is supposed... This is simulating what the light is supposed to do, but this is sort of like an approximation. But this approximation looks arguably better than this one in this case, right? So sometimes, the point here is that sometimes you might even prefer ambient occlusion. So don't underestimate it. It's actually a pretty powerful concept. So how are we going to compute ambient occlusion though? Well, we can compute using ray tracing. Very easy. So with ray tracing, I'm going to look at all directions over the SEM sphere and see if they are occluded. So up to a particular distance, right? So I'm going to trace all of these rays up to a particular distance, and if they're occluded, I'm going to say that that direction is occluded. If they're not occluded, then I'm going to say they're not occluded. So I can have a certain number of rays. Let's pick a number. I don't know, 100 rays, send in all directions over the hemisphere, and I can tell what percentage of them are occluded. Based on that, I can tell what my ambient occlusion value is supposed to be. All right, of course, you just put them in the integral, and then you sort of estimate the value of that integral with some finite number of samples. So this is a proper way of computing ambient occlusion, but it's a little bit of a problem here, because the thing is, this is becoming a little too close to computing indirect illumination. I mean, if I'm going to send, I don't know, 100 rays in all directions and find if they hit anything, I might as well just go the next step and compute indirect illumination, at least one bounce of indirect illumination, right? I mean, yes, computing indirect illumination is still going to be more expensive, because you're gonna find hits with all these rays, and then you're gonna have to shade those points and figure out how much light is coming from all of these directions. Yeah, it's going to be more expensive, definitely. But this is getting a little too close, right? Yeah, it is cheaper, but at the same time, I'm not getting the same results. So is it really worth it, right? I mean, I might as well do indirect illumination. So if you're going to compute ambient occlusion like this is not going to be particularly suitable for real-time rendering in a lot of cases. I mean, it might be suitable. You might be able to do this with GPU ray tracing. It's definitely going to be faster than computing indirect illumination, but at the same time, it's not going to give you the same quality. So it becomes like a, do I want it? Do I not want it? The choice becomes a little unclear. So we need a faster way of computing ambient occlusion if we're going to use it for real-time rendering, right? And that's exactly what I'm going to show you now, how we can compute this ambient occlusion. Now I'm just going to tell you at a high level, that is, we're going to use screen space ambient occlusion. The idea is actually fairly simple. So instead of using ray traced ambient occlusion like this, which gives you the correct ambient occlusion, I mean, I find it difficult to call ambient occlusion correct, because ambient occlusion itself is sort of a fake term. But this is properly computing that ambient occlusion integral with some ray samples. This is approximating it using some screen space techniques. Now, there are multiple ways of doing exactly this screen space ambient occlusion, or SSAO. The idea for all of them, the common thing for all of them is is that for each pixel here, you'll look at the neighboring pixels within some radius in pixels. Like, let's say I'm going to look at pixels within a 9 by 9 pixel range. Okay? And by looking at those pixels and their depth values, I'm going to try to guess if those pixels are occluding this pixel that the one in the middle. Okay, I'm just gonna, for each pixel, I'm gonna look at the neighboring pixels, and based on their depth values, I'm going to estimate whether or not those pixels are creating any occlusion. Now, this is not that easy to do because there's going to be things like these columns, right? These columns on either side. Like, oh, this one's actually a pretty good example, right? So you could say that the neighboring pixels have very different depth values, but I don't necessarily see that in screen space. I'm not sure that there's a column here. I just know that there's a particular depth value, right? So I don't know if there's anything behind this column here. There may or may not be, but I don't see it in screen space. So computing that ambient occlusion around discontinuities like this, depth discontinuities like this, becomes a little bit tricky. And so you can use different sort of heuristics to sort of approximate ambient occlusion. So this is going to provide an approximation of this ambient occlusion. It's not going to give you the exact value. You cannot do that because you don't have enough information. But this is going to be so much faster than actually doing ray tracing and figuring out that ambient occlusion, right? And if you ask me, just look at this. This is actually a pretty good approximation of this. So yes, in the end, you get an approximation of an approximation. So ambient occlusion was an approximation to begin with. So with screen space ambient occlusion, we're getting an approximation of that approximation, but it's so much faster than anything else. Now, this is actually very, very fast to compute. And so I'm getting something, by doing that, I'm getting something that is so much better than constant ambient. So much better than constant ambient. So I should probably use it, right? I mean, I'm not comparing this to indirect elimination. Maybe I'm comparing it to properly computing ambient occlusion. And I'm going to say it's pretty close, right? So if you look at constant ambient, everything looks flat, versus ambient occlusion, screen space ambient occlusion, it's looking pretty good, right? So that's where the saving is. So when we talk about ambient occlusion, we typically use that for interactive real-time rendering. For offline rendering, if you're going to compute ambient occlusion using ray tracing, you might as well compute indirect illumination and get proper global illumination, right? In most scenes, that's what you will prefer. But for interactive real-time rendering, that might be a little too expensive. Remember, we have like 15 milliseconds to compute each frame. So computing indirect illumination might be a little too expensive depending on what kind of scene we're rendering, what kind of GPU we're using. So in such cases, we might prefer ambient occlusion, specifically screen space ambient occlusion, because this is going to give something that is a huge improvement over constant ambient term. Huge improvement. But it's going to be very close in terms of computation cost to a constant ambient. This is not free, obviously, but it's very, very fast. Right? Now, this particular example is taken from this paper that's doing multi-resolution screen space ambient occlusion. So it's computing the ambient occlusion in multiple resolutions. This way you could combine results with different ambient occlusion radius, and you combine them all together and you get a nice approximation of ambient occlusion this way. So as I said, there are various ways of computing ambient occlusion, various methods of using screen space ambient occlusion. This is just one of them, and it's producing pretty good results. I actually really like the results of this paper, but there are actually other even more recent papers on this topic as well. All right. So it's a very commonly used technique in video games today. So whenever you don't have the computation power to compute indirect elimination and get a proper global elimination solution, something like this, a form of screen space ambient occlusion would be the go-to solution, because that would provide a huge improvement over constant ambient. All right. So it's a very commonly used technique because of that in video games. All right. So that's what I plan to say about screen space ambient occlusion. Again, I'm not giving you the details of exactly how these images are formed. I'm just telling you at a high level what they do is they look at neighboring pixels, the depth values for the neighboring pixels, and they sort of estimate, they assign an estimation of occlusion along that direction. So they try to estimate that integral, because you can't properly compute that integral. So I'm explaining it at a higher level, and there are different techniques. They work slightly differently. There is no standard way of doing this, actually. Each technique would be slightly different in how they compute the screen space ambient occlusion values. Let's move on to our second topic for today. Now, I talked about how to sort of approximate indirect elimination using this ambient occlusion. In the same lines, we're going to talk about how to approximate soft shadows. All right. So let's start with where soft shadows are coming from and how to properly compute them first. Now, soft shadows, what are they? So, hard shadows, soft shadows. Hard shadows with super hard edges, soft shadows with really soft and nice edges. Now, why do I have soft shadows here and hard shadows over there? Well, maybe I was lazy. I just used a simpler algorithm to compute this and a more complicated one over here. Yeah, but there's a reason why you would expect to get soft shadows in the scene. I would argue that this is probably more realistic, maybe. And I'm saying probably because depending on what the scene is, actually that one might be more realistic. Yeah. So hard shadows are stuff that you would expect to see when you have very small light sources. So if I have point light, I would expect to get shadows that look like this. Or if I have a light source that is really, really small, maybe not necessarily point, I would expect to get hard shadows like this. Or if my light source is not necessarily really small, but is far, far, far away, then I would expect to get hard shadows. But if my light source is relatively large or relatively close, then I'm going to start seeing soft shadows. Yes, area lights. So you get soft shadows when you get something like an area light, right? An area light like this, you would expect it to form soft shadows on surfaces like that. Oh, there's an interesting comment about the previous slide here. It's saying that the specular here is pretty small. It's not very large. It's a very good catch. So, yes. So here's my question. How many of you actually noticed that the fact that the specular here is pretty small? It's actually the same size as that one. Some of you did maybe, but I'm guessing not all of you. So soft shadows are related to area lights, and we're going to talk about why they're related and how they're computed and all that. The size of the specular also depends on the size of the light source, right? Remember when we talked about the specular, I told you this is the reflection of the light source. So if the light source is big, the specular is supposed to be big as well. But this is, I would argue that this is a little harder to notice. Shadow difference, super obvious. But just making this specular a little softer and larger, that's going to be a little less obvious. Now, I mean, you could see it on the sphere. On these other objects, it's very, very hard to see the difference, right? So area lights have two types of effects. One is that it's going to impact your illumination because light is not coming from one direction now. Light is coming from a range of directions for an area light. And we talked about that before. And that changes how you do shading. Yeah, if you want to use area lights properly, you're going to have to consider that, definitely. But the other thing that area lights do is that they change the shadows. And that part, I would say, is very, very obvious. So even if you will ignore this area illumination coming from an area light, you should not ignore the soft shadows created by an area light, because if you apply shadows like this, that area light is not going to quite look like or feel like an area light anymore. Right? So this shading, maybe you can get away with it. Shadows, not so much. I would say shadows are quite a bit more important for realizing that you actually have an area light source. All right, so the question is, why? Like, I have this area light source. Like, why am I getting some soft shadows like this over here? So let me show you. Let's pick a point here. Let's say this point. Now this point is it in shadow? Now when we have hard shadows, there's a very clear answer to that. We either say yes or no, right? In this case, is it in shadow? Well, kinda. I mean, it's not completely in shadow, but it's kinda in shadow. Well, what does that mean? That means that this point is seeing a part of this light source. Now, when we have hard shadows, we were saying if a point sees the light source, it is not in shadow. If the point cannot see the light source, that some object is blocking it, it is in shadow, right? In this case, it's partially in shadow because this point is partially seeing the light source. It's not seeing all of the light source, because if I take a look at the light source from this point, if I just go to this point and look at the light source, then I am going to see that, oh, there's this thing in between. It's blocking some of the light coming from the light source. It's not blocking all of the light, but it's blocking some of the light, right? So if I just look at the light source from this point's perspective, I will see that some of this light source is occluded, so shadowed, and the rest over here is visible. So this is the occluded part and this is the visible part. All right. So if I'm going to compute soft shadows properly, I am going to have to figure out what percentage of this light is covered. Now, we're simplifying a little bit. We are not necessarily worried about doing proper shading from this light source. All right, we're just looking at what percentage of this light, what percentage of the total light is covered. So I don't care about which portions, like is it on the right side of the light source, is it on the left side of the light source? I don't care about that. All I care about is what percentage of the light source is covered, because I'm only interested in computing the soft shadows. I'm not interested in computing proper lighting from area light sources. In this instance, we're just trying to compute the area. The percentage of the area that is occluded, the percentage of the area that is visible. Now, how am I going to do that? Well, if my objects are simple like this, like I have a circle and a box, I might be able to analytically compute this area. That would be fine. But in a lot of cases that we're dealing with in a 3D scene, this is going to be a little more complicated. So figuring this out geometrically is going to be kind of tough, right? It's not going to be that easy. It's going to be actually quite difficult and expensive. So here's what we're going to do. A typical way of doing this is, well, you guessed it, ray tracing. Ray tracing is like the solution to everything. Right? It really is. So in this case, the way that we're going to handle this is that we're just going to send rays to this light source. All right, from the point that we're shading, I'm just going to send rays. And from this view, these rays will look like points. So I'm gonna pick some random points on this light source, and I'm gonna send shadow rays to those points. And if those shadow rays hit something like this sphere before they reach the light source, I'm gonna say they're blocked. And if they reach the light source without hitting anything, then I'm gonna say, all right, they're not occluded, so I can see the light from those directions. And then I'm gonna count. How many of them reached the light source? How many of them did not reach the light source? Then I can tell, then I can approximate what percentage of this area is visible, right? So it's just that I'm just approximating it by counting the number of rays that ended up on the light source. Fairly simple. A good approximation works actually fairly well. This is the standard technique for computing soft shadows using ray tracing, and with that we can generate some really super realistic looking soft shadows like this one. And that will be if you have enough rays to compute this, then you're going to get a very, very good approximation, and it's going to converge to the correct result in the end, right? So ray tracing, good, we have a solution for that. But if you compute this properly, you are going to get this nice looking soft shadow. But of course, that's going to cost you, right? It's not for free. You're going to have all these rays. If you have a point light, then you're going to have this hard shadow that's much easier to compute. Well, guess what? I don't even need to use ray tracing here for point light. I could just use shadow maps. I've done that before, right? We've all implemented shadow maps. Yeah, so that's I know how to do that. That's fairly easy. But over here, when I have an area light source and I'm getting this soft shadow, I can't use shadow maps anymore. Yeah, that's kind of boring. So one way people thought about how they could sort of do this with shadow maps was, how about I just picked some random points on this light. Let's say I pick 100 points, okay? And then I generate 100 shadow maps. And then I combine them all. So it's as if you're sending rays to those 100 points. It actually works. It works pretty well, actually, if you do it that way. Although, well, first of all, it's going to be quite expensive, because 100 might work. 10, probably not, right? So you're going to have a lot of shadows. You're going to have to compute a lot of shadows too. And then you're going to have to, at runtime, you're going to have to evaluate a lot of shadows. So that's going to be quite expensive. And in the end, you might actually get some visible artifacts. So you may actually see 100 hard shadows behind this pole instead of seeing a soft shadow. Yeah, 100 separate hard shadows is what you might get. But okay, don't give up yet. Don't give up yet. We like shadow maps, okay? So we want to use some form of shadow maps to approximate soft shadows. We're going to approximate soft shadows by using some form of shadow maps. That's the goal. Now, we cannot exactly produce these soft shadows, but maybe we can approximate them, because in the end, I just want something that looks soft, right? I mean, can you tell that this is the correct light source here that produces this shadow that I've been showing you? It absolutely isn't. I just drew this light. I don't even know what light was used for rendering this, but I'll look at it. It looks okay. I don't know if it's supposed to be this big, maybe larger, maybe smaller, maybe closer, maybe further away. So, but I can tell that there's a light source along this direction, and I'm supposed to get some soft shadow like this. So maybe approximating it is good enough, right? Maybe I don't have to be exact. Maybe just an approximation is what I'm looking for. So let's go there and do that. So the way we're going to do that is that we're going to use something like shadow maps that will give me these hard shadow boundaries, but that's not what I want. I'm going to use that and see if I can recover something that looks like soft shadows, starting with hard shadows computed for a point light. Right? That's the goal. And the algorithm that I'm going to tell you in a bit detail about how to do this is going to use this shadow map idea, and it's going to be particularly using this idea of percentage closer filtering. Now, we looked at percentage closer filtering. You'll remember with percentage closer filtering, this is a shadow generated using percentage closer filtering. What we were doing is that we said, oh, we can't just do shadow map filtering by filtering the depth values. That didn't work, right? That didn't give us any shadow filtering. So what we ended up doing in the end was percentage closer filtering. That is, you, for each pixel, for each sample, you look at the neighboring 4 depth values in the depth map and evaluate the shadow separately for all 4 of these depth values. So you're going to get shadow, no shadow, shadow, or no shadow decision for all 4 of them. And then we interpolate that shadow and no shadow decision. Right? Basically, the idea is that you compute shadows from a shadow map at multiple different locations. So what we used was the 4 closest depth map texels. That's what we used, right? But the concept is a bit more general, right? I can say, I am computing shadow from a shadow map at some different locations on the depth map, and I'm just interpolating their values based on how far they are from the point that I'm computing. Right? So that's the general idea. The particular variant of percentage closer filtering we talked about last time, was just looking at the neighboring 4 depth map texels, right? It was very much like bilinear filtering. It was doing bilinear filtering of shadow decisions, right? But this idea of percentage closer filtering can be extended fairly easily and say, I'm just going to look at a number of shadow samples within the radius in the shadow map, and I'm going to evaluate shadows for each one of them separately. And then I'm going to get a weighted average of them. And that weighted average is going to give me my estimated shadow value. So I can take percentage closer filtering, and maybe instead of doing like in a 2x2 region, or 1x1, like bilinear filtering region, I can extend it to a larger portion of the depth map. And I can, for example, I can look at a 9x9 region around the pixel, around the ideal sample location. And in that 9x9 region, I can compute the shadow values, and then I do a weighted average of those values. And in a 9x9 region, if I look at a 9x9 region, it's going to blur my shadows a little bit, right? Because I'm sort of getting an average of multiple different values. So as I'm getting close to a hard shadow boundary here, I'm going to start blurring that because I'm looking at a 9x9 region. All right, so this is the idea of percentage closer filtering. It's fairly easy to extend this idea to this, right? You just use it, look at a larger area. And when we do that, actually, this is exactly how shadow maps are used for offline rendering. For interactive rendering, we typically do this because hardware can do this for us fairly easily. This is quite a bit more expensive, right? Because I'm looking at a 9x9 region. That means what? 81 shadow tests instead of 4? Yeah, it's going to be quite a bit more expensive. So what people typically do is that you don't look at all of the depth values in that 9x9 region. You sort of randomly pick some of them. You're like, I'm going to randomly pick, let's say 10. Okay? I'm going to randomly pick 10 of them in a 9x9 region. That's going to give me some approximation of what this is going to look like. It's going to be a little bit noisy because I'm randomly picking samples, but it's going to be much more efficient to compute. But so going from here to here is fairly easy. And what happened here is that I got soft shadows, right? So this was hard shadows here. Soft shadows here. Problem solved, right? It's excellent. Isn't it excellent? Isn't it wonderful, beautiful, and soft? No? You're not convinced? Yeah, there's a little bit of a problem though. With typical realistic soft shadows, I would expect the shadow over here to be a little bit harder, right? And the shadow over there a little bit softer. So this is not soft enough over here and not hard enough over there. So just picking some constant value, that did not work. So maybe I can sort of adjust the percentage closer filtering size based on where I am in the scene, and that could give me nice shadows. So that's the idea of percentage closer soft shadows. And with that, you can get pretty nice looking shadows. Then these will not match the results of ray traced soft shadows, but they are giving me the visual appearance of that, right? So there's soft here, hard over here, looks pretty good. And in some cases, you can't even tell if they are properly computed using ray tracing or just percentage closer soft shadows. Now the question is, how am I going to use what percentage closer filtering radius I'm supposed to use? How am I going to pick that radius? Well, am I going to pick that percentage closer filtering size? Well, that's the big question here. All right, let's look at that. So here's the idea. Now, you will recognize that if the object is close, if the occluder is close to the point that let's say I'm computing shadows on this plane. If the occluder is close to this plane, then I'm going to get hard looking shadows, right? Shadow edges will be hard. If the occluder is sort of further away from this surface that I'm computing, where I'm computing shadows, then I'm going to get softer shadow edges, right? It all depends on where the object is. So I am going to try to figure that out. So I'm going to compute, let's say, shadow maps for this light source, right? With shadow maps, I have a depth map, right? For any given point here, I can just look up what corresponding value I have in the depth map. So that would correspond to basically looking at a ray that goes from this point to the light source. I'm not tracing any rays. I'm just looking at the depth map value that corresponds to this point. We did that for shadow maps, right? So I have a depth value. Let's say the depth value corresponds to this point in the scene. Let's say I have a depth value in the depth map that corresponds to this point in the scene. That means that I probably have an object here, right? So now I know if my object is this far from the point where I'm computing the shadows, right? If my object is that far, and if my light source size is something like this, I can sort of figure out what kind of filter size I'm supposed to use. All right, so this is the idea. So this is how blurry the shadow should be if my occluder is over here at this distance. So basically, the percentage closer shadow maps is going to look at how far the occluder is in comparison to how far the point that I'm trying to compute is. And based on that, and considering the light source size, the approximated light source size, it's going to generate a filter radius with a very, very simple equation. And with that filter radius, I can just filter my shadow maps based on that, using that percentage closer filter size, and I get soft shadows like this. Pretty good and pretty neat, right? Very nice. One problem though. What if my object was a little off? What happened now? Well, if I look at the depth map value for this point, I'm going to find this point itself. There's no occluder, right? So this is not supposed to be in soft shadow, but actually it is, right? Because, yeah, this object is not at this point, it's not blocking this point, it's not blocking the center of the light source, but it is definitely blocking these parts of the light source, right? Still blocking the light source a little bit. So I'm still supposed to be in a little bit of shadow here. It's not fully seeing the entirety of the light source. So what that means that I cannot just rely on the occluder distance that I find that corresponds to this point. So what I need to do is what is called an occluder search. So what I'm going to do is I'm going to find out where this point is on the shadow map. It corresponds to a point on the shadow map. And then I'm going to look at that point, but I'm also going to look at points around it within a radius and see if I can find any occluders. Are there any occluders within this radius? If there are any occluders, then I'm going to try to figure out, oh, are these occluders actually casting any shadows? And if they are casting any shadows, I'm going to say, okay, I found an occluder at this distance. And I'm going to look at a user-defined region, let's say a 15 by 15 pixel region inside the shadow map. I'm going to look at all of these depth values or randomly pick some of those depth values and find if I can see an occluder. And if I see an occluder, then I'm going to need to compute the occluder distance. Well, now I'm going to have potentially 15 different occluder distances, or however many I'm looking at. Let's say I'm looking at 10 of them. I'm going to have 10 different occluder distances up to. How am I going to compute my percentage closer filtering size? Well, I could take an average of them, right? So that gives me an average occluder distance, and I can blur things out based on that average occluder distance. So yes, this is not going to be a perfectly accurate way of generating soft shadows while we're approximating them. But in actually most cases, percentage closer soft shadows work pretty well, right? So even an example like this, relatively complicated objects with different shadows, it works really well. The problem with percentage closer soft shadows is not that it's not perfect. It really isn't perfect, but it's not its biggest problem. Its biggest problem is that it's not very cheap. I mean, it might be cheaper than tracing rays, yes, but it's not very cheap after all, because I'm going to have to do an occluder search within a range, and then I'm going to have to do percentage closer filtering within a range, and that percentage closer filtering size might be a little large, right? So places like here, I'm going to have a large filter size, right? Because shadow is supposed to be really, really blurry, really soft. So there's a bit of cost associated with percentage closer filtering. It's not going to be, so percentage closer soft shadows, this method is not going to be as efficient, as fast as just computing regular hard shadows. But it gives you soft shadows. So in that sense, it's pretty good. So this is just one example of how we could compute soft shadows using a method similar to shadow maps. There are a bunch of different methods. I list them under the name soft shadow mapping. These are some of the earlier ones. The variance shadow maps, the convolution shadow maps, exponential shadow maps. The ideas with these methods is that instead of doing a sort of easier to understand approach of percentage closer soft shadows, they are trying to approximate this percentage closer filtering results. Instead of doing the percentage closer filtering and paying the cost of doing percentage closer filtering, they implement different forms of pre-filtering. So they filter the depth values, and using those, they sort of approximate what the filtering result would be. So I'm not planning to get into the details of these methods, but not terribly important unless you're particularly interested in one or all of these methods. But they're just using different formulations for approximating the result of percentage closure filtering. So they're approximating this, which is an approximation of its on its own. So as you can expect, they're not perfect. So if you look at some examples of variance shadow maps, convolution shadow maps, or exponential shadow maps, you'll see that they produce like different artifacts here and there. So these shadows, I'm not sure if you can see that they're actually, this part is darker than this part, and there's no reason for that. There's some shadow edges over here. So they're not going to be perfect, okay? But they are much more efficient than percentage closure filtering because they can actually do the shadow computation without having to go through all this extensive search and really expensive percentage closure filtering that percentage closure soft shadow method does. So they're going to be more efficient, but probably the results will be prone to more artifacts. These are some examples of the original methods. There are actually follow-up research work on these methods that provide some solutions to some of these problems. So you can say, okay, I'm getting this sort of a problem with variance shadow maps. Can I solve this by sort of specially handling this sort of discontinuities? So yes, there are methods that sort of specifically try to fix different parts of these methods. So there are more complicated methods, and the goal will be getting something that is efficient as possible, and getting something that produces good looking shadows in your particular scene. So what method to use really depends on what kind of scene that you're rendering and what kind of artifacts, what kind of artifacts you can get away with, what kind of errors are going to be important for your application. Right? But I want you to know that different variants of this sort of idea, soft shadow mapping, as I call them, that they exist. Beyond that, there are other methods that do things that don't quite look like shadow mapping at all, but they provide soft shadows. For example, you could compute distances, assign distance fields to all objects, and then do something like a simple ray tracing like lookup in that signed distance field. Signed distance field is basically saying in a volume how far a point is from the nearest surface. And it is signed, that means if you're inside the surface, it's negative. If you're outside, it's positive. That's typically how it is. So by using them, you can fairly efficiently trace occlusion rays and figure out if you're in shadow or not. And if you are in shadow, like you can look at a particular range of directions and figure out shadow. So there are all sorts of different techniques for computing soft shadows, or approximating, I should say, soft shadows used in interactive computer graphics. But this percentage closure filtering, I'd say, is like the fundamental one that I want you to know in a bit more detail. But I also would like you to know that others exist. And if you're interested in this topic, you can find quite a bit more details with more recent methods. Basically, the point is, there is no perfect solution. There are different solutions, and you pick which one works for you. But you get the idea. Basically, there are soft shadows, there are proper ways of computing it, which is ray tracing, pretty much always. So whenever we have a problem about rendering, what's the right way of solving it? Ray tracing is the answer. But there are ways of approximating it, and I just want to give you some examples of doing this. I had no intention of trying to cover everything that people ever proposed about soft shadows. That would be a very, very long lecture, and not necessarily particularly interesting, I would say. Well, if I talk just about one or two, that could be interesting. But going through all of them, I don't know, that would be too many. All right, I'm gonna end it here, and next time we're going to be talking about transparency, alpha testing, and alpha blending, how to handle transparent objects. Next week, we're going to be talking about transparent objects and volume rendering. That's going to be our topic next week. Once again, thank you all for joining. I hope you enjoyed this lecture, and I'm going to see you all next week. All right. Bye, everyone.